recording. So currently we should be online and we can start share the screen. So I would like only to remind that the last model we applied previously was the model that presented H as covariate. It means continuous independent variable, and as the coefficient was negative, so we interpreted the impact of H on the usage of internet in the following way. So it seems that the older you are, the less is probable, the lower is odd that you will be internet user. And this odds ratio, if I go back, was 0.9 to 7 for 1 year increase. And as far as you remember, we tried repeatedly for age to include another interpretation. So it means to compute changes such as 20 years, etc. And it was based on the computation that we copied this value into Microsoft Excel environment, and then we computed 20th power of this value. That's one option. Another option is to take coefficient, it means this estimate, minus 0.076 multiplied by 20, and then exponentiate both these computational procedures can be performed in Microsoft Excel environment, or of course using calculator as well. So that's about previous example. And now we should add some more variables into our model. Before we start to entering independence, I would like only briefly to recap that last time we discussed that gender should be employed in the model, that maybe also financial income of household should be employed, and last one variable, size of the city or village should be employed as well into our model. So we have still space for 1, 2, 3, maybe, and also education. So 4 new variables that could be included into our model. One brief comment, if I go back into the dialog for logistic regression, so JASP is differentiating independence that are continuous. JASP call these variables as covariates, and then treats separately variables that are nominal or ordinal and call these factors. As you can see, these pictures describe the situation quite well. So if I would like to enter covariate, it must be defined as a continuous variable or scale, and for factors, these must be defined as nominal or ordinal variables. For our case, maybe it will be quite good to check definition of variables. So gender is defined here as ordinal. That's maybe a mistake. Maybe it should be defined as nominal. So I will change this definition. So currently it is okay. Education is defined as ordinal variable. It seems okay. Then financial income is defined as ordinal, as it has quite a lot of categories, but my proposal would be maybe to change this definition into scale, as there are a lot of categories in this variable. So you can check there are quite a lot of categories, currently 15, and there is also 99 for decay. So maybe it would be good to define this variable as scale, as if I would perform logistic regression and this variable should be treated as factor, we would have 14 dummy variables, and it would be very, very difficult to interpret results. And maybe one more step should be also performed here, and this is this 99 code. We can check that this 99 is maybe treated as a valid value, and if I would include this 99 code into my computation, I would make mistakes. So maybe first of all, I will check descriptive statistic for this variable. So I would go into descriptives and then ask for description of f_inc variable. So I can check it. And you can see that here in this variable, as I expected, there are only 13 missing cases. So these are 60 missing cases. And if I ask for frequency table, it seems to me that this code 99dk is treated as valid value. So before I start to compute anything, I should omit this code 99dk from this variable. So we will start with introduction of definition missing values in JASP. So I hope it would work. So if you go here to the left upper corner of JASP and find preferences, and here option data, here you can ask for some missing values. So I guess that if I click here and type 99 and click plus, so code 99 should be included. So now JASP is not responding, so I will wait for a second and I hope it would work. I guess that you know whether it works or not on your computers currently. Does it work on your computers or not?
Yes.
Sorry?
Yes.
Yes? Okay. So
yes, it works.
I need to wait. You can check once again frequency table, and 99 should be currently omitted from computation. So please check it before my computer will start to work properly. So it seems that my computer decided not to go for today's lecture. Sorry for that. Okay, so now it seems that everything should be okay. So I will try to skip outside from this option. So here it is. And now, as you can see, 99 is correctly defined as missing. So it seems that currently we should also include this variable into my computation. So I would go back and we discuss about change of the definition of this family income variable as continuous scale. So I would change to scale. And this is the last step we should perform on this data. So once again, my JASP is fighting. Sorry for that, but I know that there are some troubles with my computer, so I hope we will be able to continue. So that's a change of definition of family income, and now we would include variables into a model, and then we would discuss about results. So before my computer will start, I will only briefly recap the contents and the presentation. So we would be discussing currently about individual coefficients. So it means once again we would be discussing about odds or odds ratio. We will also discuss about pseudo R-squares and about so-called likelihood ratio test. And then we will be discussing about tests for individual coefficients. These are usually called Wald tests in logistic regression. And we will be briefly discussing also about standardized coefficients. So I hope that currently everything is okay. So I would go back and I will make a copy of previous model with age as covariate. So let's make a copy. And currently I will include a model with more independent variables. So here it is. And now, before I start, I will only check whether standardized coefficients are included. They are not, so I would skip into statistics. And I would ask here for standardized coefficients as well for input. And you can also ask here for so-called confusion matrix. I'll explain what is it about, and maybe it is better to use this confusion matrix in proportions. So please ask for proportions here. You can also check that in this dialog for statistics, there is also residual diagnostics. This is similar to linear regression. So you can ask for big standardized residuals. You can ask for cases with big Cook's distance. I will not recap all this stuff, but these problems of finding some extreme values and influentials is the same stuff as for linear regression. So that's about residuals, and we will ask also for plots. So please visit also plots option. And according to my opinion, a very nice plot for JASP options is the first one, which is called Inferential plot, display conditional estimates plots. So if you can ask for this chart, as this is quite good option for interpretation of our results graphically. So I will ask for displaying of these conditional probabilities. And now I can close plots, close statistics. We will skip the option of model. As far as you know, this option allows you to include interactions into a model, but we will not apply any interaction. And I will ask for inclusion of another independent. So first of all, I will include gender. Next one variable would be education level. And last two variables included into a model are family income and size of the city and village. So now JASP will be briefly recomputing our results. Of course, family income is continuous, and gender, education, and size are categorical variables. And I hope that quite quickly JASP will offer results for analysis. So, okay, so at least in my case, part of the results can be seen from the screen. So here I can go at least to the table with basic results. So I can see coefficient for age, family income, gender, currently category female. Then we have here education, 3 dummy variables, and dummy variables for city size. So here we have automatically, in comparison with linear regression, prepared dummy variables for gender, education, and city size, which is quite pleasant from JASP. And let's start with interpretation from the first figures. So first of all, for family income, the value here of the estimate, once again, this coefficient is presented in logits, is 0.154. So can anybody help me to interpret this positive value of relationship between family income? And currently we are preparing model for logics of internet usage. What does it mean if this coefficient is positive? What is the meaning of this positive coefficient in logics?
That I think that as the income of your family increases, the chances that you have an access to the internet also increases.
Yeah, that's correct interpretation. Thanks a lot. And if we go back to the previous discussion about family income, it was originally categorical variable, but 15 categories were included, so that's why we can treat it as continuous variable. So this odds ratio 1.167 says that if the category of family income increased by 1 unit, so then odds ratio are increased by approximately 1.17. Once again, for better interpretation, but I will not start these computations once again, for better interpretation would be some bigger chance in family income. For example, I can take 5 categories as 1/3 of distribution of family income. So 5 categories would mean that I would take this 1.167 and I would take 5th power of this value, and I would see very impressive value of the impact of family income on internet usage. So you can try it alone, but this is for a simple analogy to our previous computations for age computation here for internet usage, as well as for age that were included also in the model for Titanic survivors. So that's about family income. So these two are continuous variables. For the age, negative impact, and for family income, positive impact. I guess that these impacts are quite conform with our previous expectations. Next one variable is gender, and it is called gender female, as JASP automatically take the second category. So you can click here. Second category of our dependent variable as the category for which computations are treated here, and the first one would be our reference. So you can see originally 1 was female and 1 was male and 2 female. That's why female are compared to male. So similar logic is applied for education and size. So it means that the least educated people and people from the lowest villages are reference category for the next comparison. So first of all, gender and female, it means female compared to male. And as the coefficient is negative, 0.332 with minus, and also odds ratio is below 1, 0.7. So it means that for female, the chance or odd to use internet would be lower than for male. If I would like to compute it and interpret it substantively, it would be quite good strategy to take this 0.7 and make reciprocal value. It means 1 divided 0.7, and I guess that 1 divided 0.7 is approximately 1.4. So you can try to compute it on your computer or calculator. So I will try to check it, and the precise value would be 1.4285. So once again, it means that odds ratio for internet usage for male is 1.4 times higher than for female. That's one possibility. An alternative possibility would be that for female, 1.4 times is higher odds ratio to non-use internet. So I can reverse categories of dependent or independent to use odds ratio that would be above 1. So that's gender and comparison of male and female categories. For education and for size of the city, the situation is slightly difficult in comparison with previous, as I'm not using only one variable here, but I'm using for education 3 and for size 5 categories. The reason is very simple. Originally there were 4 and 6 categories for education and size, and that's why currently I'm using 3 and 5 dummy variables. Once again, these are prepared automatically, and the first one category is omitted by default. I hope that you remember that in JASP, if you would like to change this reference category, there is a very simple option. I would go back to data matrix, I would click into description of my variable, and I would change only order of individual codes. But it's not necessary to apply this step currently. So I would go into education, secondary without state leaving exam, secondary with state leaving exam, and tertiary. And the category which is omitted is elementary education. So it means he or she didn't achieve secondary education at all. As you can see, all these coefficients are above 0. So it means if I compare people with secondary without state leaving exam with state leaving exam and tertiary educated people to reference category, it means people with no secondary education at all. So for all of these categories, odd or probability as well to use internet is higher. You can see also that these coefficients are quite different. First one is quite small one, close to 0, but and the second one and the third one are quite big one. If you recompute these estimates, so it means these coefficient in logit scale into odds ratio, so you can check very easily that for secondary educated without state leaving exam, the odd to use the internet is 1.2 in comparison with those who achieved only elementary education. But for those who achieved a state leaving exam on secondary level, also who achieved tertiary education, these odds ratio are much higher, 5.2 or 6.3. Once again, not to be misleaded in the interpretation by odds ratio, it means estimates that are valid only for a sample. We should maybe go to the last 2 columns, which are 95 confidence interval for odds ratio in this case. And you can see that maybe for those who are secondary educated without state leaving exam, there is no difference to those who are elementary educated, as this confidence interval is included 1, and 1 means there is no relationship at all. So maybe that this impact of secondary educated without state leaving exam is not proven. For the second and the third category, we can see that maybe our previous expectation about 5.3, 6.3 were maybe too optimistic, as it can be as low as 3.3. So these are lower bounds of both of these confidence interval, but it can be also as big as 8.6 or 12.2. So you should read as well these confidence intervals for better understanding of your results. So it means that sampling error is included here into the computation of confidence interval. So that's about education, and maybe that we should also omit this category education secondary without state leaving exam, and we can maybe merge this category to elementary educated and leave it as reference category. That's maybe conclusion from this first analytical insight. Next set of variables is based on sizes. So it means the second lowest category, the third lowest category, etc., up to the biggest cities in the Czech Republic. And as far as you can see, these coefficients are mostly positive. So it means that for bigger cities especially, and maybe also for middle-sized cities, odd or probability to use internet is higher than for the lowest villages. If I would once again like to read results, I would go to this column for odds ratios. And once again, it would be nice also to see confidence intervals, and maybe you can check that some differences are maybe not observed in the population, as these confidence intervals sometimes really include value 1. Once again, 1 means there is no relationship at all between predictor and dependent variable. So that's all for this discussion about these estimates, odds ratios, and confidence intervals for odds ratios. And before we would go further, there are 2 more columns that should be discussed in this table called coefficients. First one column we should briefly discuss is standardized coefficient column. Once again, this is not default output. We need to ask for this output. So here in statistics, we ask for regression coefficients in standardized option. So that's why there is new one column which is called standardized. Standardized coefficient are offered for us to have an option to compare the impact of individual independent variables. As originally, these variables do not follow the same scale. Age starts at approximately 12 years, and the last one respondent is, I guess, approximately 19 years old. Financial income, it goes from 1 up to 15. And all the rest, it means gender, female, education, etc., are coded as 0, 1. These are classical dummy variables. So the length of these scales is totally different. So that's why I'm not able to compare these estimates. I'm not also able to compare these odds ratios. And the only one option, very simple option, to compare the impact of these independent variables is to apply standardized coefficients. So here, if you take these variables and compare the impact, so you can see very easily that the most important variable for my data set is the age. So this is the most important predictor for usage or non-usage of the internet. You don't need to read signs here for this column. The meaning of the sign is still the same, negative or positive impact. The biggest impact, education secondary with state leaving exam and education tertiary. So education is the most important predictor. The second most important predictor is the age. And then I guess that the third one is financial income, and this category of city size. So these are some middle-sized cities in the Czech Republic. Then there is also quite big coefficient for these villages from 2 to 5,000 inhabitants, and the rest is quite small. So maybe that from substantive point of view, the rest variables should be omitted from my computation. So that's insight from standardized coefficient. And the last one coefficient, column in this table, which should be presented, is a column which is based on Wald test. So there is Wald statistics. Once again, this is computed as estimate divided by its standard error, and for statistical reasons, second power from this ratio is computed. So that's Wald statistic. That's why here it is written there are degrees of freedom, as usually for Wald statistics we are applying chi-square statistic, and chi-square distribution must have its degrees of freedom. So for one variable there is only 1 degree of freedom. And here we have recomputed p-values. So once again, classical description of p-values would be based on some predefined level of statistical significance, usually called alpha, and we are comparing this predefined alpha with our computed p-values. So if we would apply classical level, such as 0.05 level, so we should treat as age, financial income, also gender, also the impact of secondary with state leaving exam, tertiary education, and maybe, but it is somewhere on the border, city size from 20 up to 90,000 inhabitants, as some impacts that can be generalizable to the whole population, and the rest, as p-values are quite big one, are maybe not statistically proven effects of these independence. So this is the discussion about p-values. Once again, I would like to warn you about too much too much impact on p-values. Currently, there are many recommendations in statistical literature. Try to avoid p-values, try to avoid expressions such as statistically significant, insignificant, etc., etc. But this is also some information about my data. Once again, I would like to repeat that nearly the same information you can find here in confidence interval column. If p-value is below 0.05, it means that this confidence interval is not included one. So that's only alternative option how we can assess the statistical importance of individual predictors. So these are p-values. So we have discovered all this stuff, and maybe if I would like to conclude in my case, my recommendation for maybe minor changes for this model would be, I would take education variable with category secondary without state leaving exam, and maybe I would merge this category to elementary education, as it seems there is no difference from substantive point of view and also from statistical point of view. So maybe I would merge these two categories. And maybe there would be also space for these city sizes for some merges, as maybe some categories are not quite different from each other. For example, this second category of city size from 1,000 up to 2,000 is maybe not very different from the smallest villages below 1,000 inhabitants, so they could be merged, etc., etc. So that's insight into these results by individual coefficients and their odds ratio, standardized coefficients, confidence intervals, and p-values. Now let's go briefly to the first table that is presented as model summary. So here, first of all, we can compare our model, so that's model called H1, this model including only intercept. And for this comparison, we can apply AIC information criteria and Bayesian-Schwarz information criteria, so-called AICs and BICs. The rule is that the lower level means better model, and as you can see here, the difference between AICs or BICs is quite big one. Here it seems approximately more than 400 units. Here it is 440 units if I'm computing well. And very simple recommendation is that if there is a difference at least 10 points, so the model with lower value of AIC or BIC is better. So we can be pretty sure that from statistical point of view, we are going right way. So it means that our model is much better than the first model we have applied. So it means model with the intercept only. So that's a comparison of two models using AICs and BICs. We will be using these statistics in next lectures as well. So that's why we are discussing about this step. And then next step is formal statistical test following chi-square criteria. This is usually called here in logistic regression as likelihood ratio test. And logic of this test is very simple. It is using this value called deviance. It is based on likelihood value of the first model and likelihood value of the second model. This deviance is only minus 2 times logarithm of this likelihood. And the difference between these deviances is following approximately chi-square distribution. So that's why this difference currently is 580 points approximately. Degrees of freedom are computed here, so 1142 and 1131. The difference is the same as the number of rows in the table of coefficients, and according to this difference, which is I guess 11, chi-square is evaluated by p-value. Null hypothesis for this so-called likelihood ratio test, as it is computing the difference or ratio between these likelihoods. So the null hypothesis says that no of these independent variables influence our dependent variable. So it means no predictor is necessary in my model. That says null hypothesis. An alternative hypothesis says that at least one of these predictors can be, from statistical point of view, useful. So it is total analogy to overall f-test in linear regression. So here, as p-value is quite small one, so we can conclude that it seems that at least one of our predictors seems useful. And we know that there are a lot of useful predictors such as age, family income, education, etc., etc. And for linear regression, if we try to summarize our results, so it means if we try to describe the relationship between dependent and independent variables, we usually compute so-called R-square. Sometimes it is called coefficient determination, etc. And now it would be nice if somebody could repeat what is the meaning or possible interpretation of this R-square in linear regression. So what is the meaning of R-square?
That used variables explain 32% of internet usage.
Yeah, but what is correct interpretation of R-square in linear regression? I usually multiply by 100, interpret in percentages, and how I would interpret this statistic.
The fused model explains 32% of chance to access an internet.
Yeah, I'm not asking to interpret this current value. I will change this interpretation in a few minutes, but I would like only to hear that classical linear regression R-square says this is the percentage of explained variance of dependent variable by independent variables. And Here, as we are discussing about binary logistic regression, so it means the case in which we have a variable with only two categories, we cannot apply such simple logic as there is no analogy to variance for continuous variable for binary variable. Of course, there are some measurements of variance for nominal and ordinal variables, but this is a slightly different discussion. But here, these so-called McFadden-Nagelkircher and Cox and Snell R-squares are not definitions of variance. These coefficients are usually based on some comparison of our model based on this deviance or likelihood ratio from which deviance is computed, and for likelihood value for null model with the intercept only. So these coefficients are designed from 0 up to 1 and are comparing model with our predictors to model with no predictors at all. So we cannot follow the interpretation of explained variance or another explained step. We only know for these, and I call these as pseudo R-squares, so these are not R-square in total, so we only can interpret it as the value between 0 and 1. 0 means no explanation at all, 1 means the model fully explains differences for dependent variable. And now, as you can see, there are more than one formula for computation of these pseudo R-squares. So there is formula from McFadden, Nagelkircher, Cox and Snell. You can find approximately 10 different formulas in the literature. So I will give you only some brief recommendation what should be applied. So in social sciences, the most common strategy is usually to apply Nagelkircher R-square. So if you would read articles and books applying logistic regression, so you can usually find Nagelkircher R-square. So this is the most common coefficient. And currently, there are recommendations to replace this coefficient by so-called pure R-square. This is one of the newest coefficients, and that's why JASP producers implemented also the computation of this coefficient. But once again, it is impossible for interpretation multiplied by 100, interpret in percentages. There is no such interpretation for these pseudo R-squares, so it should be clear to all of you. Okay, so that's all about this table, and now we would go to two last outputs that are prepared for us. First of all, there is something what is called confusion matrix. There are different wordings of this output in different software packages, but what is the meaning is quite simple to guess. Here it is in rows. There is situation what is observed in my data, whether somebody is non-user or user of the internet. So this is real status in my data, non-user and user. And this is prediction from my regression model. So it means that logistic regression can be also applied for prediction. And these are predicted non-users and these are predicted users. Ideally, if my model would be perfect, I would predict all non-users as non-users. So here I would have some figure. I would also predict all users as users. So here I would have another figure, and these two would be zeros. But as you can see, approximately 39% of my file is correctly computed as non-users. 39 are correctly predicted as users, but approximately 11 and 12 percentages in my data are incorrectly predicted as users if they are non-users, or users if they are non-users, as non-users as if they are users, sorry for that. So approximately, if I sum up 11 and 12, 23% in my data are incorrectly predicted by my model. If I recompute a percentage of correct classification or correct prediction, so 1 minus 0.23 or 100 minus 23 in persons means that approximately 77% are correctly classified and the rest are incorrectly classified. This is also another possibility how we can evaluate the quality of our model. So it means more than 3/4 are correctly predicted, classified from my model, and approximately 1/4 is incorrectly predicted. And this statistic can be applied, especially if I would be comparing more than one model. So maybe I would take this set of independents, I would take different set of independents, and I can compare these two and say which model is better. So that's a performance diagnostic by confusion matrix and computation of percentage of correctly classified cases. There are also many different computation statistics for this stuff. So if I would go here into performance statistics, the so-called AIC, sensitivity, specificity, precision, F measure, Breyer, H measure, etc. But we wouldn't go into these details, so I would skip it. So here we have only so-called confusion matrix. And last one, output, which is quite nice, and usually different statistical packages wouldn't follow this output. This is output in the form of so-called conditional probability plots. As you can see here, this is the age scale in my data, and this is the probability of usage the internet. And as you can see, as this S-shaped curve is going down, it means that as the age is increasing and increasing, the probability of internet usage is decreasing and decreasing. And as we are applying logistic regression model, this is S-shaped logistic curve, so this relationship is nonlinear. I would add 2 questions, and if somebody can help me solve this puzzle, I would be happy. First of all, there is some gray area around this line. So what should be the meaning of this gray area? That's my first question. And the second question is, this picture is showing the impact of the age and how another independents such as education, family income, etc. Are treated in this picture. Do you have some idea what can be the importance of another predictors in this chart? So some solutions to these questions. What could be this gray area around this S-shaped line?
Perhaps gray area can be confidence interval.
Yeah, you are definitely correct. That's confidence interval for the estimation. Okay, nice. And the second question was related, okay, we are here changing age and computing probability of usage internet, but what could be the level of another independence such as family income, gender, education, etc.?
Like how can it look like?
Sorry?
How can it look like for
no. This is computed for different ages, probability of usage of internet, and the question is, in this original model, we included also family income, gender, education, size. So what could be values of these variables that are not presented on this picture? As the model is quite complex, this is not including only age. So I wouldn't longer ask you about this question, I would add you an answer. So JASP, and according to my opinion, this is maybe not the best option, takes all the rest independent, such as family income, gender, etc., and take the values of all these independents at 0. So this chart or another charts that are presented here are computed for different ages, but the rest of independents are set at the value of 0. And for some of these independents, 0 doesn't have any meaning. So maybe that this chart is sometimes not very good to interpret. But at least some basic patterns you can recognize from this chart. So once again, as age is increasing, probability of usage is decreasing. As family income is increasing, probability of usage of internet is increasing. And JASP will also offer for you similar charts for categorical variables such as male, female, education, and city size. So you can see here these points. So these are estimates of probabilities, and these bars, errors bars are confidence intervals once again. So you can see, for example, that very similar situation is for elementary and secondary without state leaving exam educated, and for elementary with state leaving exam and tertiary educated. There is no big difference for male and female according to this picture. And you can see here that also for city size, there are no huge differences. So maybe that biggest impact is included in age and family income variable. So these are probability charts. So that's all about presentation of results in JASP. So I would save this output for your future usage as the last step today in JASP, and then we can leave JASP. So I would close it. So that's all about binary logistic regression in JASP. And now only for brief insight, I would skip into M+ environment, and I will show you how you could perform binary logistic regression in M+. So it is, sorry for that M+ demo. Here it is. Before I start to run the model in M+, I will only show you a bigger picture of input file in some text editor. So here it is. So it is much better. I hope to see, maybe we can also add one more bigger size. So here it is. So, first of all, it's not obligatory, but you can add some title. So here I type logistic regression usage of internet. Necessary part is to define my data file. As my data file is called D2 logistic regression data.dat. That's why I'm defining this file, and it would work without definition of the folder or disk on your computer, only in the case in which input file is in the same folder as my data file. So here it is this situation, so that's why it's not necessary to also describe paths where my file is saved on my computer. Next one is definition of variables. So this is the same data file as we were applying. So there is variable age, gender, education, usage, DOM 1, 2, 3, financial income, size, and education categories for dummy variables are presented here. So that's all what is present here. Then there is definition of categorical variable. So if I'm applying logistic regression in M+, I need to define that dependent variable is called as categorical. And categorical for M plus means I would be treating, instead of linear regression, logistic regression. Then I need to define variables applied in my data analysis. Once again, demo of M plus can compute only models with a maximum 2 independents. So here I am applying only model with 2 independents, financial income and education, and use internet is dependent variable. Then the section for definition of missing values. And for logistic regression in classical settings, we are applying maximum likelihood technique. So that's why I'm typing analysis estimator is equal to maximum likelihood, in shortage ML. Next one section is about a model, and I am applying model for usage based or dependent on financial income and education. So that's why I'm typing use on financial income and education. And special outputs that are not presented by default are standardized coefficients and confidence intervals. So if I ask for these 2 outputs, I would get standardized coefficients and confidence interval in my data. So I would close it now I would try to open it in M plus demo. So I would try to open this file. So here it is. And now I need to run these commands. So I hope it would work. Computation of logistic regression is slightly more intensive in time than linear regression, as some more steps called iterations must be performed, but I guess that in few seconds computation is finished. So here I would go down to our basic results. And if I would use maybe this presentation for these results, so I would make a copy to here. So here I have model results in classical logic scale. So this would be original logic scale for my results. So first of all, I will make these figures bigger. So these would be coefficients for individual predictors. And if I would like to estimate logistic regression odds ratios, there is another output included here. There are also standardized results included here, and also confidence intervals for original coefficients as well as for odds ratio. So this is only brief insight into M plus environment. And as the last chapter today, we will make brief introduction also into alternative models for logistic regression. So if your dependent variable has more than 2 categories, it can be nominal or ordinal. We will briefly discuss about nominal variable case, and this case is called usually polytomous or multinomial logistic regression. Once again, unfortunately, JASP cannot handle such models, so we will not show example in JASP, but we will treat this model on data in Spss package. So first of all, the logic of this polytomous logistic regression is very close to binary logistic regression. The only difference is that I am not applying one equation which says logic of my dependent variable is based on independence. But for polytomous logistic regression, I am using more than one equation. And the logic is very, very close to the logic of dummy variables. For polytomous logistic regression, I would take one of the categories of dependent variable as reference category. Usually this is the last one in statistical packages. And I would take comparison of odds or odds ratios of the first category of my dependent variable and the last one, of the second category of my dependent variable and the last one, of the third category and my last one. And I'm computing repeatedly these comparison in one model. That's the basic logic in polytomous logistic regression. So if I would like to show you an example, I hope it would work in a few seconds. We would take a similar example to our previous one. We were defining internet usage. Currently, I'm applying similar data about using internet and library as well. And we would try to define model for usage of internet only, library only, internet and library together, and also non-using library as well as internet at all. So currently Spss is opening on my computer, and I can show you how it works to perform this polytomous logistic regression in Spss environment. Once again, JASP cannot handle these models, but you could perform these models in M+ environment. M+ is capable of all these models, so you should try it if you like at home. So if I would like to perform this polytomous logistic regression in Spss, I would go into Analyze, and I would go into Regression, and here and there is a model of multinomial logistic regression. So here it is. So here I would need to define dependent variable. For me, it is internet and library usage. Original categories that are present here are, I am not using anything, library only, internet only. I'm using internet as well as library. So I would need here to take this variable and to decide which category would be reference. Maybe I'm not using anything would be my reference category. So I would take internet and library. Once again, sorry for that. Linear multinomial logistic, so internet and library, and my reference category would be the first one, which were coded as 1. So this is our dependent, and independents are called factors and covariates. So this is nearly the same strategy as it was presented in JASP. And I would take, for simplicity, for example, the age variable as covariate, and maybe I can take also income as covariate, and maybe I can take also student as factor. So it is expected that maybe students will be more often using internet, and libraries, maybe people with higher income would be using more often internet and libraries, etc., etc. So I would perform this model, and we can very quickly see results only to see what is the logic of presentation of this polytomous logistic regression model. So nearly the same stuff as for binary logistic regression. We can compute so-called pseudo R-squares. We can also compute likelihood ratio test. So these are first 3 tables here, and then we have quite long table with so-called parameter estimates. As once again, we are comparing one category which is omitted. Once again, here I'm not using internet as well as library with all the rest. So library only, internet only, and both. So we have 3 sets of coefficients here, and all these sets would be comparison to those people who are not using library as well as internet. So, for example, those who are using only library, according to the age, as the impact of age is negative, it seems that the older you are, it seems you are not using library. Higher income means that if my income is higher, or maybe it is family income, I'm user of library in comparison of the option I'm not using. And for students, it is negative, so it means that student is 0. This is not student, so it means that students are using library more often. For internet only, similar pattern. Also, the age negative, income positive, and for students negative. So once again, internet users will be usually younger, with higher income, as students will be using internet, with those who are not using anything, internet and libraries. And using both internet and library in comparison with those who are not using anything. Once again, the pattern is quite the same. So the age would be decreasing of usage of both internet and library. Income is increasing, and students will be usually those who are using both in comparison with those who are not using anything from these two options. So I can maybe also summarize these patterns into one pattern that income, age, and students are maybe predictors of using library, internet, as well as both of these equipments. So this would be very simple example of polytomous logistic regression. So I'll close it as we wouldn't need it anymore.
Sorry, an intercept in that case is meaningless, yes?
Sorry?
Intercept in that case is meaningless.
Is what?
Meaningless. That it doesn't make any sense to interpret intercept in the previous table that you showed in SPSS.
Intercept for these models would say what is the level of probability, level of odd ratio for this comparison, and usually it doesn't have any sense. You are right, yeah.
Thank you.
Okay, I would skip this description about SPSS options, and I will only briefly discuss about the last one model, which is ordinal regression. If your dependent variable has more than 2 categories, and these categories can be ranked from the lowest to the highest, there is also another option to apply ordinal regression models. Once again, SPSS or M+ is capable of these models. In JASP, you cannot find this option. Unfortunately, in real life examples, usually these models are not very often, as there must be fulfilled some condition which is called parallel lines, and for most of data this condition is not fulfilled. So this is very, very rare to apply this model. Only to say what is the difference between previous polytomous and ordinal regression model. So the biggest difference is that I am not preparing these comparisons with some reference category, but I'm using one equation, and only in these equations there are different so-called thresholds for different categories of this ordinal variable. So only one equation with thresholds is applied in ordinal regression. So I will skip all this stuff, and last one comments are only related to closed techniques, to techniques that were covered in previous discussion. I would say that the closest neighborhood of binary or ordinal or polytomous logistic regression is so-called discrimination analysis. This is the technique which is very, very close. So it means dependent variable is binary, nominal or ordinal, and sets of independents are continuous or categorical variables. Also, very close technique, and we will cover briefly this technique in this course, is linear analysis, which is mainly designed for categorical data. So there are no continuous variables at all, and special type of these models are called logistic analysis. Very close technique to discuss the logistic regression is also classification and regression trees. This is graphical technique mostly designed for categorical data based on regression methodology. And there is also a procedure that can be applied to all these techniques that are prepared for binary nominal or ordinal dependent variables, and this is called ROC curves. And these ROC curves are capable of comparison of classification quality of different models. So currently I will close the presentation. So I would stop showing the picture and stop